How to measure strain in materials accurately. Imagine trying to catch a tiny ripple in a pond after throwing a stone. Now, think about doing that with a material under stress. That's what measuring strain is all about. It's about detecting those tiny changes in shape or length when a material is loaded. Getting this right is key to understanding how and when materials might fail or break down. So, how do engineers and scientists do it with precision? Let's find out. First, understanding what strain really is helps. Strain is the ratio of how much a material stretches or compresses compared to its original size. It's a very small number, often expressed as microstrain, which is 1/1,000,000th of a strain. Measuring this tiny change accurately is essential because small strains can lead to big failures if not caught early. The most common tool for measuring strain is called a strain gauge. Think of it as a tiny, flexible metal grid that sticks to the surface of the material. When the material stretches or shrinks, the grid stretches or shrinks too. This change causes a tiny change in electrical resistance, which can be measured with sensitive electronics. The trick is to select the right size of the gauge. Smaller gauges, like those measuring 0.2 millimeters, are perfect for high-speed tests or small areas. Larger gauges up to 30 millimeters work well for concrete or thick materials. Installing the strain gauge correctly is very important. It must be bonded smoothly without air bubbles and aligned exactly in the direction of the expected strain. Misalignment can give false readings. Temperature also plays a role. When it gets hot or cold, resistance changes, which can distort the data. To fix this, engineers use special strain gauges that compensate for temperature changes or apply techniques like using two gauges, one as a reference, to cancel out thermal effects. Wiring is another detail that matters. Using 3 wires instead of to helps reduce noise and interference, especially over long distances. The circuit should have a stable power supply and high-quality amplifiers to pick up the tiny resistance changes accurately. Calibration is also key. Before testing, the system is calibrated under conditions similar to the actual test to ensure accuracy. Optical methods like digital image correlation are also used. They track surface patterns on the material with cameras to measure strain over larger areas. These are great for complex shapes or large deformations, but are less precise at measuring very small strains. They are also limited by camera resolution and frame rate. When it comes to accuracy, strain gauges are the go-to for small, precise measurements. They can detect strains as low as a few microstrain and are reliable up to about 5% strain. Optical methods excel at measuring larger strains, up to 100%, and can give a full picture of how a material deforms across its surface. Using these measurement techniques helps engineers see how materials behave before they break. They can spot stress concentrations, fatigue points, and other signs of impending failure. This knowledge helps design safer structures, improve materials, and prevent mechanical breakdowns. In the end, measuring strain accurately is about catching tiny changes early so we can understand and improve the durability of the things around us.